Let's get started. Today we're gonna go ahead and start with our Unit 3 material. Um, let's start off with related rates. The first part of related rates is a review of implicit differentiation. Now we can separate terms with addition and subtraction. We can't separate terms with multiplication and division. Vocabulary like blank per blank and at a rate of blank, both and will, for this context, mean derivatives. So let's talk about this problem. This problem is just a review problem. It states find dy over dx for this equation. Well, we know we apply dx on this whole thing. We split up to every adding and subtracting term. So we get d dx of x plus d dx of 3xy. Then minus 2, or well, minus d dx of 2y squared is equal to d dx of 2. However, we know that we cannot just put d dx on x and y. The 3 will escape, but remember product rule, and also keep in mind quotient rule as well. It will split it, but it won't split it as plainly as addition subtraction does. So let's go left to right. This one, we know that answer is just going to be 1 here, or because we're still reviewing, let me write like what happened. So from here to here, this was power rule. Then from here to here, we take the constant out, but then we also do the product rule. And we got d dx of x times y plus x d of dx of y. Then over here, this is another glorified power rule. And then we know that the derivative of a constant is just going to be 0. Okay, so hold on, let me adjust this real quick. Hello. Then I'm going to go ahead and perform these derivatives over here. We got 3 times 1, so I'm just going to write 3y plus 3 times x times dy over dx. And then that gets multiplied to minus 4y is equal to 0. And then from here, oh, I forgot. Remember, y is a function of x. So even though we did the power rule, we also need to do the chain rule and multiply by dy over dx. dy over dx. So we want to find dy over dx. We put them all, or we keep them all on one side by themselves. So when you get rid of this, that becomes -1, -3y. Factor out the dy dx. We got 3x minus 4y dy over dx is equal to -1 minus 3y, and then divide that out. So dy over dx is equal to -1 minus 3y over 3x minus 4y. All right, let's keep it moving with another example. Find dy dx for this expression. Xy plus y is equal to 8. Right? So we apply it to everything. xy plus dy or dx d over dx of y is equal to d over dx of 8. That's a product rule, so we're going to go ahead and do x dy over dx, and then plus d of dx of x, which is 1 times y. Here, we know that's going to go straight to it, dy over dx is equal to the derivative of a constant, 0. So now when you go ahead and keep all these terms, with dy and dx is on one side, so we're just going to get rid of that minus y over here. And then we'll factor this out. And then we're left with negative y over x plus 1. Okay. So this is just a review of implicit differentiation. This is not the like message of this section. Excuse me. Right. So in this section, we're going to go ahead and change notation slightly. Instead of having x as our input, we'll have t as our input. Given that t is our input, we'll be differentiating with respect to t instead of with respect to x. Now, what's going to happen here is that we're going to be using common formulas. The area of a circle, circumference of a circle, area of a rectangle, volume of a sphere, volume of a cube, volume of a rectangular box, volume of a cylinder. And we're going to assume that all of these variables, non-constant variables, that they have some kind of shift with respect to time. However, before we do that, let's just practice the math behind doing it. So let's pretend that all of these variables are some function of t. If they don't have, the only variable that's not a function of t is ones that involve constants. So let's try it over here, example 3. So these are all functions of t. We're taking derivative of t, so that means we get d of dt of a is equal to d dt of L times W, which we know is just product rule. Derivative of the first one times the other one, and then plus derivative of the first one times, the regular term L times the derivative of the second one. So then you would have that as your answer. And there's no simplification we take beyond this. The gimmick here, and the part that looks confusing, is that we technically have 3 functions of t. Now, in your homework and in this material, we won't get too crazy about it, but it's good to just pretend with these hypothetical examples. Over here, this is the area, this is the area. This is the formula for circumference. And we're going to assume that the unknown variables are functions of t, so just that c and r. dc of dt is equal to 2 pi dr dt. Remember, pi is not a variable, it's a constant. That means a specific entry, and then we know 2 is a constant, so it's a bigger issue. Here, it's going to get a little bit more complicated, but still very manageable. We know the left-hand side is going to be dv dt, which I'm already going to write, but we know that we're going to have a product rule stacked on top of a power rule. So let's go ahead and do derivative of this guy first. So it's 2r times dr over dt, and then times the second term untouched, and then adding it to the first term untouched times the derivative of the second term, which is just dh over dt. Now all is equal to dv over dt. Alright. So now we're going to introduce ideas where these guys are going to be functions of time. Now keep in mind the verbiage. If it says blank per blank at a rate of blank, that's going to mean that we input that numeric value for its variable's derivative. So we're told that the length of the square changes at a rate of blank, then that means that we're putting that as a derivative. So keep that in mind, okay? Let's start. A pebble is dropped into a calm pond, causing ripples. The radius of the outer ripple is increasing at a constant rate of 1 feet per second. When the radius is 4 feet, what is the rate of the total area changing? So they want to know what the rate of the total area changing. So they want to know what dA over dt is. So we need that formula. What are we exactly using the formula of? Well, it's the ripples of a pond. So that must be in the shape of a circle. So the area of a circle. So we're going to start here. And then we're going to take the derivative of this whole thing. dA over dt is equal to, oh, we're kind of just using this, I guess. 2 pi r, and then times dr over dt. So that's the formula at the moment. However, we need to solve for dA over dt. Well, we know 2, we know pi. But we technically don't know r, or we don't know dr over dt. But it gives us r and dr over dt. It gives us the radius. But it gives us that the radius is increasing at a constant rate of 1 foot per second. And it gives us that when the radius is 4 feet, what is the area? So that means that we need to pay close attention to what goes where. Well, it says the radius is 4 feet. So that is, we're just going to plug into the radius here, 4. And then, okay, let me use highlighters for a minute. And then it says that the radius is changing at a constant rate. So that means we plug in that entry for the derivative of the radius. So this, again, this whole constant rate verbiage means that we're plugging in here. So that means we can simplify this into 8 pi. So it says, what is the rate that the total area is changing? The answer is 8 pi. It's changing at a rate of 8 pi. You could add per second, but I'm not going to be that big of a stickler for these couple of things as we're learning along. The homework will grill you on that. Let's keep moving. The radius of a sphere, okay, so now we're dealing with the sphere, is increasing at a rate of 9 centimeters per second. Find the radius of the sphere when the volume and the radius are increasing at the same rate. So they have upped the ante just a little bit. Okay. First, we need to recall the area of a sphere, which I should have just take. Let's see. Okay, the area of a sphere. Right here. I'm sorry, not the area of a sphere, the volume of a sphere, but you guys get my point. Okay, so we have V over 4 over 3, or equal to 4 over 3 pi r squared. Wait, r cubed, excuse me. Okay, so now it's for sure going to matter what we consider r squared and what we consider dt. Let's apply the derivative. Here you get dv over dt. On the right hand side, the constants all escape. you'll do a product. You'll do a power rule, and then you have to do the chain rule. dr over dt. We can simplify this into 4 pi r squared times dr over dt, dv over dt. Okay? So now we need to figure out what we want to see. This time we were told this is the formula we're using because right away we're being asked about, a sphere. All right, so let's go ahead and get some highlighting done. Let's read this from left to right. It says, the radius of the sphere is increasing at a rate of 9 centimeters per second. So that means this is going to affect this dr dt. Then it says find the radius. So that means that guy is actually going to be the unknown. So we need to solve for r equals. Okay. Find the radius of the sphere when the volume and the radius are increasing at the same rate. So this is a hidden trick almost, where it's telling us what the volume is increasing at a rate of, but it's not literally telling us what that rate is. It just says are increasing at the same rate, which we're told in this context, it's at 9. So in this case, they both are the same thing, and you can proceed to plug both of those values in as 9. 9 is equal to 4 pi r squared times 9. So now you need to solve for r squared. Well, right away, I can simplify this whole expression by dividing out that same exact value since they both have 9. 1 is equal to 4 pi r squared. And then I can go ahead and solve for r squared. R squared is equal to 1 over 4 pi. And then I take the square root to solve for r. I get r is equal to plus minus the square root of 1 over 4 pi. Two things can happen here. Well, not two things can happen. Two things should happen. The order doesn't matter, I guess. For one, you know that it has to be plus because we're measuring distance. And then two, we can split the square roots. So we have square root of 1 over square root of 4 pi. The top part only gets simplified to 1, and the bottom part only gets simplified to 2 square root of pi. So our answer is 1 over 2 square root pi. I guess you could have stopped here now that I think about it, but I leave it up to you to just keep that in mind, especially for the homework where you may not get that chance. All right. I believe this one is our last one. So now we have the air is being pumped into a spherical balloon. Okay. At a rate of 800 cubic meters per minute. Sorry, I forgot the question. Um, how fast is the radius of the balloon changing when the radius is 30 centimeters? So for this one, if it's a spherical balloon and they strictly do mean spherical, then we are dealing with the same formula. So I'm going to copy and paste this format right here. dv over dt is equal to 4 pi r squared times dr over dt. Okay. Now, from here, we have different values. First, it says the air is being pumped into a spherical balloon at a rate of 800 cubic centimeters per minute. So the air inside a balloon, a sphere balloon, is a glorified way to describe a volume. So this whole sentence, I would argue, is speaking for the volume. How fast is the radius of the balloon changing when the radius is 30 centimeters? So they want to know what dr over dt is equal to. But we still need to solve for r. Well, they say right here at the very end when the radius is 30 centimeters. So that means this part right here I need to plug in 30 centimeters. Okay. Let's go ahead and now plug in these numbers. We got 800 is equal to 4 pi times 30 squared times dr over dt. Okay. So we're going to have to do some solving. Let's go ahead and I'm going to start off with dividing both sides by 4. And I'll get 200 is equal to pi times 30 squared times dr over dt. I'm going to take a beat and go ahead and figure out 30 squared, which I can see is just 900. Divide this whole constant so I can get dr dt equals dr over dt is equal to 200 over pi times 900. I can factor out these two sets of zeros, and I'm left with the final answer, 2 over 9 pi. And that's my answer. The radius of the balloon is changing at a rate of 2 over 9 pi. Okie doke. That's pretty straightforward from here. The homework is what's really going to challenge you. Okay. Let's move on to the next one. So the next one is the maxima and minima. Now, this plays into a lot of technicalities for us. It's a bit odd because in a lot of practical cases you don't actually get, the tallest point or the lowest point because typically they are at infinity for some of these for some of these functions, but it's important to entertain the idea and know of the idea, especially when we are dealing in like a limited or maybe very specific framework. Okay, so let's go. Absolute extremum. An absolute maximum is the highest y value a function can attain on a given interval. An absolute minimum is the lowest y value a function can obtain on a given interval. So the extreme value theorem is as follows. If f is continuous on the interval a comma b, then there is a point on a comma b at which f has an absolute maximum and an absolute minimum. How to find the absolute extrema on a to b? First, find the critical points on a and b. What are the critical points? A critical point is an x value where the derivative of f is equal to 0 or the derivative of x is undefined. For a specific x value, keep that in mind. Evaluate f of x, the original function, at the critical points and the endpoints. Then compare the y values. The largest y value is the absolute maximum, and the smallest y value is the absolute minimum. Okay? So step 1. Find your critical points. Or no, let me read this. Okay. Find the absolute extrema of f of x equal to x cubed minus 3x squared plus 1 on -1 to 3. First, find the critical points. Well, in order to do that, we need to find f prime since it's going to be what we're using. So we're going to go and do f prime of x, which is 3x squared minus 6x, and that's it because that derivative is just 0. We're going to go ahead and factor this a little bit so we can solve for this better. I'm going to take out a 3, I'm going to take out an x, and I'm going to put x minus 2. And I want to find all the values for which this f prime of x, for all the x's that it equals 0. So using the zero product property, I can technically set 3 things to 0 because I have 3 multiplying terms. I can set 3 equal to 0. I can set x equal to 0. And I can set x minus 2 is equal to 0. This one obviously leads nowhere because 3 equaling 0 doesn't make any sense. X equals 0. There's not much to solve for. It seems like when x is 0, this will be 0. And then here, just add 2 to both sides. And it seems like whenever x is 2, this whole thing will be 0. So our critical points are 0 and 2. Now, the second step, evaluate the f of x's. Now remember, we need to evaluate not just the critical points, but we need to evaluate the endpoints as well. So I'm going to go ahead and put them in order. -1, 0, 2, and 3. Okay. Those are x's and these are f of x's. So let's go ahead and do this one by one. -1 to the power of 3 minus 3 times -1 squared plus 1. That's going to be -3. That's going to be a -3. And that's going to be plus 1. And it's going to be -3. Right, next we have 0, 0 cubed minus 3 times 0 squared plus 1. That's just going to be 1. Then 2, 2 cubed minus 3 times 2 squared plus 1. That 2 cubed is going to be 8. -3 times 2, it's going to be -12, then plus 1. It's going to be -3. And then when I plug in 3, we got 3 cubed minus 3 times 3 squared plus 1. That's going to be 27 minus 27 plus 1. That's going to be a 1 as well. Okay. So, what is my absolute maximum and minimums? I'm going to look over something. And maybe I need a typo. Okay. No, I didn't make a typo. Okay, so all right. So, um, we can go ahead and say, although it's a little weird, like we can say that the absolute maximum is actually at both endpoint or at both points, -1 and 2, and then the absolute minimum is also at 2 points, 0 and 3. Okay. Okay. Let's see. Now, this is great and all, but we also have to talk about different types of extrema. So we're going to call it local or relative extrema. A relative maximum is the point where a function changes from increasing to decreasing. A relative maximum is a point where the function changes from decreasing to increasing. These occur at critical points. So these just signify moments on the graph where there is a sort of hill or a pit being formed. So that again, if my function starts increasing and then it starts decreasing, you're making a little hill where this can be a relative max. If your function decreasing and then all of a sudden starts increasing, you're creating a little dip. And that could be a relative min. Okay. All right. let's go ahead and now talk about them in a different light. So we're going to talk about this idea of finding the relative max and minis on a first derivative test. So what is a first derivative test? A first derivative test analyzes how f prime of x changes sign around critical points. Remember, derivatives tell us slopes. So positive slope, that's going up. Negative slope, going down. So find f prime of x, find critical points, make a sign chart for f prime of x. For making a sign chart, we talked about that in pre-cal technically, but if you don't remember it, or it's been a minute, or you didn't talk about it in pre-cal, we're gonna go ahead and just quickly review it today. So let's go ahead and find f prime of x. First thing I'm gonna do is I'm gonna go ahead and, or here for this prompt, find the relative extrema of this function. Okay. So for here, f prime of x, it's not going to change too much. The only thing that changed was this +2. But either way, it still didn't matter for this evaluation. And then it says find the critical points. So we're going to go ahead and solve for this function is equal to 0. So 3x squared minus 6x is equal to 0. And we are going to take advantage of the factoring. And we get our critical points. X is equal to 0 and x is equal to 2. Now we're going to go ahead and make that sign chart. So what you're going to do is you're going to go ahead and mark the critical points. So 0 and 2. And then you're going to pick values in between and on the outsides of 0 and 2 that are easy to evaluate. And you're going to just quickly gauge the sign of the function. Now, typically you can factor this if you like. If you're doing this straight from pre-cal, you know that this is just, you would do one for each of these. So what is it? 3, x, and then x minus 2. And then you would plug in all of these values. Let's pick a value to the left of 0. Let's just pick -1. In between these two, 1, and then outside 3. So this is going to be pretty straightforward. For constants, we know that it's just the value of that variable, which is just 3, so positive, positive, positive. For here, it's x, so we're just putting those values, so negative, positive, positive. And then we have x minus 2. So when I plug in -1, it's going to be negative. When I plug in 1, it's going to be negative. When I plug in 3, that will be positive. So the combined function, two negatives make a positive, so positive. There's one negative only, so it's just negative and positive. Okay. So this tells us that it was increasing and then decreasing. And then it's decreasing jumps to an increasing. We're going to go over these bullet points because I may have skipped them. I think I skipped them. I apologize. F prime. F prime changes from positive to negative, then f of x has a relative maximum. If f prime changes from negative to positive, then f prime has a relative minimum. If f prime doesn't change sign, then there are no relative extrema at that point. So, give me a second, I'm gonna sneeze. Okay, hopefully you didn't hear that because I muted myself well. We see that from here to here, we jump from positive to negative. So that means that x equals 0, there is a relative maximum. And from here, we jump from negative to positive. So that means that x equals 2. There is a relative minimum. Which, funny enough, for our previous problem, we did reach a similar conclusion with 0 and 2. 0, we said that it would be a minimum. From 0, wait. Oh, that's interesting. Is this a typo? Right. Oh, that's so funny. I swapped 3 and -1 here. Oh my gosh, I am off my A game. I am so sorry. And I wonder if you're all doing this. I hope you all do this live with me, but I wonder what it's like waiting for a typo live because you can't interrupt a recording. That's interesting. Okay. Well, I mean, the logic still stood, right? It's just that I read 3 and 1 instead of -3 and 1, and that does indeed switch the game, right? Okay, I'm gonna let this air dry real quick, but you are swapping this value for min and this value for max. And the funny part is that it's what I intended to with the notes. So, I mean, it's been a while, so I guess it's what I get, right? But what are you gonna do? I'm human too. I'm allowed to make mistakes. I don't know if you all know that. I hope you all know that. I hope that's obvious from the not to be isn't there a meme? There's a meme of like a Jimmy Kimmel where I think it's Michael J. Fox and he like reacts like in his square, but like he's the only one like reacting around his square and they didn't even put him in the middle and he's reacting like he's in the middle. So it's like kind of cringe. Where was I going with that? I don't know. I'm human. I promise. Pinky swear. Pinky swear. Pinky swear? Pinky swear? Okay, cool. Alright, so that's gonna be the absolute I forgot. No, it's gonna be absolute min. It's gonna be the absolute max. Okay. Alright. Next, let's try the second derivative test. The second derivative test analyzes the concavity at a critical point to determine the nature of the extrema. Find f prime of x and solve f of x is equal to 0. Then find f double prime of x and evaluate f double prime at each critical point. If f double prime of that critical point is positive, then it concaves up and the critical point is a relative maximum. If the f double prime is negative and it concaves down, then the critical point is a relative maximum. Now, for these, the verbiage, it kind of, it's okay, it doesn't shift, right? Like, if we're gonna be honest, it technically doesn't shift, but, how's a good way to put it? It does look weird, right? We can all agree it looks weird because up, max. It's not max, it's min. Down, max, min. Wait, what? What's going on? Right? Like it does you can accidentally pick up a pattern where the pattern is incorrect because because of like a regular, not crazy human association. So what we do is when we say concave up, we draw a huge U. And then when we say concave down, we draw a huge N. And visually, before you do anything, you can see a concave up. So that means it caved up. I mean it up shape. Right here. Up shape. Oh wait, no, I should do it for the people that only watch the vertical videos. And then if it concave down, that means it concave down. Oh, I can't do that. It concave downward. Oh, like this. So if you do the trick of this, then you could sort of visualize it with an extra point here and an extra point here, that's going to be a top point. That's going to be a max. you could do here is a bottom point. That's going to be a min. So this is to sort of help you, figure that out. Okay. There's a typo here. Oh, I forgot. Okay, this is a solve for f prime of x is equal to 0. Okay. All right. So let's start. Find the relative extrema of x to the power of 4 minus ax squared. Oh, sorry, ax squared. Okay. So, hello, hello. Oh my gosh, I hope I didn't lose audio for that long. Jesus. Okay. All right. For the relative extrema, x to the power of 4 minus ax squared, you're going to first do the derivative, which you can see is 4x3 minus, let me just write it out in full, 8 times 2x. From here, we can combine that to be 16x. And then we're going to go ahead and solve for when this is equal to 0, but ideally we should factor this first. So I'm going to take out the 4 that they guys share, and I'm going to take out an x that these guys share, and I'm left with x squared minus 4. Well, from here, I should know difference of squares, and I have another set of multiplying things. X minus 2, x plus 2. Okay. Right. Then from here, zero product property, solving for the critical points. I have 4 things technically that can be equal to 0. I have 4 is equal to 0. I have x is equal to 0. I have x minus 2 is equal to 0. I have x plus 2 is equal to 0. This, again, similar to before, doesn't make any sense. X equals 0, that makes perfect sense. X equals 0. X minus 2 equals 0 makes sense because when x is 2, x minus 2 is equal to 0. And then same thing over here when x is negative 2, x plus 2 is equal to 0. Okay. So we found our critical points. The next steps says find f double prime. So now I'm going to do f double prime of x. So using this as a reference. Okay, let me write it down in full just in case. And then go ahead and do that. We get 12x squared, and that just becomes minus 16. Okay. Then it says evaluate each of these points at that critical point. Okay. So let's go ahead and just plug them in. I don't know why I was gonna do like a table side by side. That just makes it appear. This just makes it ugly. Uh, -2, 0, 2. So plug in here. Let's see. 12 times a -2 squared minus 16. That's going to be, what is that? 48 minus 16, which is 32. Over here, 12 times 2 squared minus 16 was, because this would be the same thing, will also result in 32. And then 0, it'll just be -16. So, because the 0 was negative, that means for x is equal to 0, since it was negative, f double prime of 0 is negative. Then we have concave downward. For x is equal to 2 and x is equal to -2, f double prime of 0, or 2 is positive, and f double prime of -2 is positive. Then we have a concave up. But remember the u and the n. This implies that there was a relative max here. And this implies that there was a relative min here. And that's our answer. Now, from an analytical standpoint, there is behaviors to how the signs of these functions behave at any point, not just critical points. So if you have the combination where f prime is a positive value and f double prime is a positive value, and then you can say that f is increasing and that you'll have a upward concavity. If you have a combination where f prime is positive and f prime is negative, but the f function is increasing, then you'll have a downward concavity. If you do negative positive, that means the f function would be decreasing, and you would have again a upward concavity. If you do negative negative, that's a decreasing, you'll have a downward concavity. So, for example, let me get highlighters out. I think this is the last thing. Yes, last thing. If we were following this function, we could say that it behaves, so the slope is going downward, so it's one of these two, but it is steadily rising, right? We can see that towards the future it is rising. So this area kind of represents this area. Then we have here that the slope is positive and that the actual trend of where we're going is also positive and it's increasing. So that means this value, this over here represents this value. And notice how in both scenarios we have a upward, we have a concave upward. Then over here we have a positive slope, but we notice that it's steadily going down. So the function is steadily going down. Even though, f of x is increasing, we know that it's trending downward. So it's going to be over here. Oh, I don't know why I'm doing that. And then last but not least, kind of because I set it up this way, we have a negative slope and we know that we're trending downward and the f is decreasing. And that means we have a concave downward. And look, with the concave downward, we have a maximum point. Okay. All right. So I'm gonna be honest. I feel like in your homework for this one, you're probably better off doing the first derivative test. I think at most the second derivative test will sneak into like an extra. Oh, how many of y'all notice? Um, my my exam questions add up to 105. So there's like a not hidden, but like there's like a little like just a wiggle room of like here's bonus question. So uh I don't know if I'm gonna do the second derivative test as like a kind of a bonus question mentality, but I do want you to just keep that in mind. Okay, just so that way you know it exists. Okay. But that is gonna wrap it up for today's video. Thank you all for being so patient. Um I'll see you all in the next video. Remember to have questions and let me know about anything, guys, okay? All right. Bye-bye.